Sound design.
So, basic RF microphone link budget. Steven, what are we doing here?
All right. So one thing that's extremely important about RF is your gain. Your gain throughout the entire system, your gain coming out of the antenna, the gain you lose going through air, essentially. And we need to be aware of all of that. And there's a way we can actually calculate this to say, is this enough power? Is this system going to work? We can get an idea instead of just guessing, which is something we don't really want to do because that leaves us uncomfortable and not confident. And then just that leaves us sweating behind the console saying, maybe it'll work. So this is the way that we can get away from that and to feel confident that we know this thing's going to be a good thing.
So, from what you just said, I'm understanding that a link budget has to do with gain staging. Is that correct?
Yeah. We're basically taking account for all the pluses and minuses, all the losses and all the gains, whether active or passive, throughout the entire system, and adding them up to see what we get at the end.
Cool. So, budget is like I'm thinking about how much money I have to spend for the month, and a link is each link between each device, right? Or each step in the signal chain.
Yeah.
Okay. You made this infographic, and I think that infographics should sort of be self-explanatory. And so what I would love to do is tell you about the things that I understand, the things that I don't understand. And then, other people watching this video as well will be able to ask questions and make comments on the video.
Great.
Okay. So first of all numbers to be in decibels. Okay, great. So I've got to start here, and then I've got to finish here at the bottom right. And this is some kind of a flow chart. So far, so good?
So far, so good.
Okay. This is great. I've got a microphone here, and TX means transmit. So the first step in my equation, I guess, is transmit power plus antenna gain. So I've got it. That's my very first number, right?
Yes.
Okay. And I guess I should go ahead and say that after we talk about this graphic, we actually have an example. So we're going to talk about it in kind of an abstract way. Not abstract, but we're going to talk about the method, and then we're going to apply the method, right?
Yes.
Okay. Transmit power plus antenna gain. So this is where on my wireless microphone, I can set normal, high, low power, or sometimes it'll say like 10 milliwatts or 20 milliwatts. Is that right?
Absolutely, yeah. So that would be your transmitter power, your TX power at that point.
Great. Okay, so I would find that out first, and then this minus symbol here means that going through the air to the receive antenna, I'm going to have some loss.
Yes. So minus going into free space path loss, which is going from the microphone's antenna, to the receive antenna, we have quite a bit of loss, and that is really the wireless link. That is the wireless section of our RF.
Okay. And I know that because I looked at this a little bit earlier, I saw this note down here in the bottom, does not include miscellaneous losses like body loss, fading, or antenna mismatch. What's body loss?
So body loss is pretty much just what it sounds like. Our bodies absorb a lot of RF energy. And so if, for instance, I have a microphone right here and I'm facing the antennas behind me and I'm facing away from it, I'm going to have loss from that. The reason I didn't include it necessarily in this infographic is that it's incredibly hard to predict.
Okay.
A lot of times we'll throw a number in there for that, which we can go over in the example, but it's a per basis type situation, and so it's not something I want to just throw in here. It's really, I don't want to say it's more for advanced users, but it's something that we need to walk on more delicately than the rest of this, which is the straightforward portion of the link budget. Got it.
So sometime in the future, there might be a whole other infographic that's just body loss.
Yeah, that'd actually be great. It's a good idea.
Okay, so the signal gets from the microphone through the air to the antenna, but it looks like I'm jumping the gun a little bit here because the antenna is down here. So the first step is actually how much loss in the air. That's what this graphic part is. Oh, I see now. So it's from antenna to antenna, and we can actually calculate how much loss I need the distance in meters and the frequency in megahertz.
Yes.
Right so far? Okay, so I would measure that distance with a measurement disto, or I guess if I'm looking at a room diagram like the day before the event, or I'm doing a site survey, I would look at the potential distance from like the farthest place on stage to wherever I plan to put my antennas.
Yeah, and a lot of times when we do these, we're looking for the worst possible case scenario. So if you know there's a point that your speaker or your artist might walk, pick that farthest region they can actually physically go to and do your worst case scenario. And then anything else under there is technically covered.
Got it. Yeah. So we're trying to come up with a conservative figure here.
Absolutely.
Okay, so we're traveling through the air. We've calculated that with this step here. And the frequency in megahertz is whatever the transmitter is going to be set to, right? So I would have had to have done my coordination ahead of time. Or is there a conservative estimate for that as well? Because I might change the frequency during the show if there's some problem or once I get on site.
I can tell you just through experience that changing the frequency in this formula doesn't change too much, but it's good to keep it consistent, or not consistent, but each one you input is fine. Or if you want to take the tuning band of your particular type of gear and pick a frequency right in the center and use that as a reference, like I said, it doesn't change too much. It's mainly the actual distance, but it's up to you how deep you want to get. I like to go dead on every time. I like to find the frequency I'm using, go exactly, just to get as close as possible. But
got it. So this number here, the distance in meters, is going to make a much bigger change than the frequency in megahertz.
Yes.
Okay, polarization mismatch. This is going to be a loss, and you and I talked about this a little bit ahead of time because we were trying to figure out how to show, because polarization is basically antenna aim, right?
So if I have an LPDA that's vertical and I have this antenna vertical, these are matched in polarization. But if I have this at 90 degrees from my LPDA, we can see that, and this is vertical, then I have a mismatch. Theoretically, 90 degrees off is an infinite mismatch. That doesn't necessarily happen in free space. So we need to add that in because there is always polarization mismatch loss. This is something that can be difficult to calculate because reflections, but we can always say that we have a minimum of 3 dB. So if you watch the previous video where we talked about our helical antenna, which has a circular polarization, there is an actual fixed 3 dB mismatch loss with circular polarization. Now, on linear antennas, if you have it 45 degrees, that math actually works out to 3 dB, which is why if you see people try and do the 90-degree angles on their antennas, that's exactly why. So a safe bet is to always have at least 3 dB polarization mismatch loss. And if you really have your antenna angled farther than that, for whatever reason, you can put it in this formula and calculate it.
Now, this is making me wonder as well. Every time I put up my LPDA shark fin antennas, I always put it vertical, straight up and down. Are there ever times when you would want to do something different? I've never seen anything different.
Yeah, so if you actually have your microphone if it's a microphone that's on a stand, it's always going to be like this because they're talking into it. You would actually get better signal if you put your antenna horizontal like that. If you don't know it, again, 45 degrees because you're halfway in between vertical and horizontal, which is going to give you that not fixed, but close enough to fix 3 dB of mismatch, which again is why a lot of people do the 45-degree angles on antennas. But if you know that your mic is going to be fixed in one location, in one orientation, then if you put your receive antenna in that orientation, you'll have a good shot of getting quite a good signal.
Got it. Okay. Yeah, that's really good to know. Now I'm trying to think about what adapter do I need for my mic stand so I can turn my antenna 45 degrees. When you're going out and you're working on shows, how are you deploying your antennas? Are they angled like that?
Yeah. I'm using LP claws, so you can angle it. Yeah.
LP claw onto a mic stand?
Yeah.
Cool.
One on a mic, actually on a rack in the mic stand. But it depends. I move my antennas around all the time.
Okay, depending on where you are.
Yeah. Just like your PA, you wouldn't put it in the same. You wouldn't say my PA always goes in this spot in every room I ever walk into. Same way, changes per room.
Okay, this is great. I'm learning a lot. So moving along here, we get to antenna gain, and okay, now I'm a little bit confused. Is this going to be a plus or a minus, or are we saying here that it could be either plus or minus?
So this is going to be a plus. So we're moving directly from polarization mismatch right over the antenna. Okay. And so we're going to be adding the antenna gain. So this next step is going to be a positive because the antenna gain should always be positive, if not zero. We shouldn't have negative in our field. It can happen. We don't need to dive into that, but okay. we're pretty much always going to have positive gain from an antenna, and that's passive gain, as we've talked about antenna patterns. I'll use this as an example again. This is going to be basically our cardioid. Because we're not radiating this direction right behind it, that radiation that is coming out this way is forced forward. And so that is our passive gain, which this is about 7 dBi. So at that point, we can use this little green plus here to add 7 to our link budget.
Oh, got it. Okay, so your like shark fin LPDA antenna might have 7 dB of gain, and then the standard omnidirectional antenna that came with your receiver should be, it's passive and omnidirectional, so it should be 0 or close to 0.
Close to 0, yeah. 2.0 or for a dipole 2.15.
Okay. Okay, so we picked up some gain with the antenna. Now we're going to lose some gain because of the cable and connector from the antenna to your multicoupler gain or loss, right? Why do we have a negative here and then a plus minus here?
Okay, so that negative is going to be loss we're seeing into the cable. And so cables are always going to have loss. You can put an amplifier in them, but you're generally using an amplifier to compensate for cable loss. Every single cable exhibits loss. In this instance, the cable from the antenna to the multicoupler, and if you're not using a multicoupler, if you don't have multiple, then that would go straight to the receiver. But the antenna coming out of the cable coming out of the antenna is generally the longest one in your system. And so we need to figure out what kind of cable that is and what kind of loss it has associated with it and subtract that from our system.
I'm seeing. So I see. So some of these things are equations that we can plug in numbers to, like up here and over here. And some of these things are just set by the manufacturer. We just look at the specification sheet and we say, okay, we have RG8X cable or whatever, and that has this amount of loss per meter per foot. We see that our cable is 10 feet long, and then we know how much loss it is.
Yes.
And you also mentioned connector, though. How significant is that? I guess I could also look at the specification sheet for that connector?
Yes, and that so cables and the connectors do break down over time. So you can look at specification sheet for whatever connector you have. Good connectors should be either no loss or about 0.5, which is what I've put in these coming up is what I put in those. Connectors that are broken down over time can be like 1 to 1.5. Hopefully not over that. That's pretty much a broken cable or a connector. But also same with cables, where they get broken down over time, they exhibit more loss.
Okay. And that's a whole other thing we could talk about, is how cables break down over time and how they are less efficient over time. So I guess we won't dive into that now, but that's a big topic, right?
Yeah, we can spend a day on that one.
Okay. Okay, so multicoupler. What is a multicoupler? Why aren't you just saying antenna distro or something like that?
Multicoupler is a generic term because it could be input or output. So the distro is what we're familiar with, which is going to be our splitter, but it's generally referring to an active splitter. So in this sense, because we're talking about a microphone, it would be a distro or active splitter. So we have one cable coming in from the antenna, and that cable is split out to maybe 4 or 8 or however many that goes into multiple receivers. And also in this instance, this is going to be a unity gain device, which means that for each, let's say if you have a split, you're splitting it 2 ways and you have 3 dB. So you're going to have the 3 dB amplifier to compensate for that to get you back to 0 at the output. So if we're using an active distro, which is what a lot of us are, then we're going to have no loss from that and no gain on the distro side. If we're using a passive one, like a Shure UA221 or a Wilkinson style or any kind of just passive split, not a BNCT, that's important, then you will see about 3 to 3.5 dB of loss there. So if you are using a splitter or a multicoupler, it's important to know what kind it is and what kind of loss it has associated with it, because we're either going to subtract that from it or we're going to leave it alone because it theoretically has, it is compensated for the loss that it creates in itself.
Cool. And is that why I want to make sure I'm not getting
minuses there.
Okay, great. That's what I was going to
say. Yeah, sorry. Jump again.
So another potential loss here, same thing. Cable loss, connector. We already talked about that. And then we get to the finish line here. And now we have these numbers, -40, -70, -90.
Yes.
And do the colors mean anything? So is -40 good and -90 is bad?
Yes, this is something I want to talk about and specify a little bit. So -90 is definitely bad. A lot of receivers that are using, their noise floor is close to -100 dB or dBm. That's not necessarily the lowest signal it can pick up. So let's say if it's -100, doesn't necessarily mean you can pick up a signal at negative 99 dB. So we want to stay away from anything getting close to negative 90, especially because in this example, we're not including these body losses yet. And so we want to get as high as possible. Now, negative 70 I put as yellow because it's definitely acceptable. So the highest level you see on most of your receivers out there, for sure, Sennheiser, is around negative 70. Now, the highest you can go pretty much is getting close to negative 40, which is going to be close to peaking, but that's a good amount of, a very, very strong amount of signal. And so I put that in green because if you have negative 40 with this example, let's say we add in body loss, and that drops us down to negative 60, which puts us above negative 70. So we have a very strong signal. So those are kind of the examples I put. Negative 70 is absolutely workable, but you're going to go start getting some areas where if you get too far away or something happens in the chain somewhere, you could have some issues. Maybe not, but negative 70 is safe. Above that is great. Once you start getting above negative 40, you might be getting a little too much, but with losses, it's hard to get that way unless you're right up next to an antenna or you have some sort of device boosting it, possibly illegally. But, so that's kind of why I put the red and yellow and green.
Got it. Okay, so at first I was thinking this didn't make sense because all I really care about is my relationship to the noise floor. But now you explaining that a lot of times the noise floor is around negative 100 for many devices, then now it makes sense that, okay, I want to be above that, at least like 50 dB, right?
Yeah, 50 is great. Like I said, 40 is great. Okay. But you start getting a little too high off that. Negative 30 you're kind of pushing it. But again, you can pull negative 30 out of this formula, but then remember to think about that you're going to have some losses with body. So.
And the whole goal, I guess we should have said at the beginning with this link budget, is that we want to hit the target. We want to hit the bullseye. We don't want to have so much gain that we have overloads, and we don't want to have so little gain that we drop into the noise floor or go below where squelch takes over and we have a dropout, right?
Absolutely. That is the goal.
And does that have to do with my colors here? So where do I hit an overload? Is that at 0?
No, it's going to be around negative 30, negative 20.
Okay.
But again, even if you pull out negative 40 from this formula, we're going to assume more losses in the actual environment. So you'll be safe with around negative 40 with what we're looking at with the actual path that we have in this infographic.
Great. Okay. Thank you for explaining all these steps to me. If you're watching this video right now and you have any questions for Steven about how he created this graphic, then please comment below. But we're not finished yet. We're actually going to go into the next page, which has an example. I just wanted to take a short break here and let you know that you can ask questions below this video, and Steven will do his best to answer them for you. As you can see, like, we're trying to simplify something that is very complex, and each one of these steps, could have a whole video about it. So ideally I want to do this before a show, but I could see how it would also be helpful, like doing a post-mortem. So after a show where I had problems, I could look at all the chain and say, okay, here's maybe where the problem was.
And actually, real quick on that, that situation happened not too long ago where I had a system that had quite a bit of loss, but it was still going to make it. But I had an unexpected amount of loss with the cable between the antenna to my combiner on an IEM side, and it actually did cause drops. And going back and looking through the system, I realized there was way too much loss coming out of that cable, and that amount of loss on that cable actually killed my shot at a clean RF show. And swapping it out is what fixed it. So yeah, you can definitely do it on the backside. When the problem has happened, you can go through and check everything and say, oh, that's what it was. So yeah, this is helpful in a lot of ways.
Just walk me through this. It looks like we're going to apply brand and model numbers to each of these steps in the chain.
Yeah, absolutely. And right now, because we're in 2019, I decided to use a ULXD4 transmitter.
Okay.
I was trying to figure out what I wanted to choose, and this one's easy. So we'll go with this one, and I think a lot of people are starting to get into these. So we're going to walk through this step by step with our ULXD microphone. And up here, I've kind of put up a situation for us to go by. So we have the ULXD4 transmitter at 20 milliwatts, which is technically that microphone's high power mode. We were at 540 megahertz, which is, I chose out because it's almost dead center of the spectrum we're allowed left in UHF, which is 470 to 608, not including guard bands and duplex gaps, which is something else we can talk about in other lessons coming up, maybe. And we have 40 feet. And 40 feet, what that means is from antenna to antenna, from the microphone to the receive antenna. So that is our actual wireless link, is 40 feet. So we have 45 degrees of polarization mismatch loss. So that means we have our antenna like this, which a lot of us have probably seen and what we've talked about a little bit if you've watched the last videos. And then we have an LPDA type antenna. So we're going to look at that and we're going to say it has 7 dB of gain, 7 dBi, if you want to be more specific. And then we have 30 feet of RG8X cable, in which in this situation, 30 feet of RG8X cable, which is frequency specific at 540 megahertz, equates to 2.8 dB of gain, of loss. And then we have, I just put in for a nice newish connector, 0.5 dB of connector loss. And then we're going to go into antenna distro or multicoupler, which is active. So we're going to have 0 dB of loss there. And then we're going to go into our little short jumper from that inside the rack from our multicoupler to our receiver, which because it's quite smaller, we can see that loss drop quite a bit to to 2.28 dB. Those points are hard to see there. Yep. And then we have another connector loss of 0.5, and then we end up back at our receiver with our final signal level. So
wow, okay, so then you added those all together here at the bottom with a final level of dB at the receiver.
Yeah, and so looking at that guide to the right with the red -90, yellow -70, green -40, so we are above that -40 with negative, and in some instances that negative could mean an overload, but what we didn't do here is body loss and other environmental losses. So an absolute minimum of at least 20. So that puts us at negative, so we're totally fine. And one thing I do want to talk about real quick is how do we figure out gain from a microphone antenna? We can definitely look at specs like this right here is a Professional Wireless Systems antenna. I can look on their website and I can see exactly how much gain they say this antenna has.
Okay, but you're talking about this step here, right? RX antenna gain?
Yeah, and actually kind of going to the TX antenna gain. So, I mean, just as a reference, that antenna that I just showed us, we can look up the website and it'll tell us what gain it has. But how do we know the gain of a microphone?
Right.
It's hard to predict. And one thing is
generally... Can you just tell me 20 milliwatts?
Oh, that's the transmitter gain. So every antenna is going to have some sort of gain or not. And so I'm using 0 dB for this antenna because it has actually a normal, this has a normal mode helical on it. This is actually a UHFR antenna. I believe it's a patch style antenna for a ULXD4, but they're omnidirectional. So they're not really having forward gain. And so I'm using 0 for that.
Okay.
And that's something I did want to point out because that's a question that how do we figure that gain number out? And there's really not there. You could use 1 if you want, but that's going to be more typical of a whip on a body pack, but it's a good safe bet to just use 0 on antenna gain for a microphone.
Got it. Okay, why does this say 13 and this says 20?
All right, so that is our conversion to dB. So if you notice in the top right, all numbers are to be in dB. If we actually make that mistake and do one in milliwatts, we're going to get a funky number that's not going to be accurate. So we need to make sure everything is in dB for this calculation.
So how did you get from 20 milliwatts to 13 dB?
All right, so we take a log base 10 of 20 and then multiply by
10. Wait, say that again?
Log base 10 of 20 and then multiply by 10 and get 20 milliwatts.
20 milliwatts.
Yep.
Log 10 times 10.
And then we get 13
dB. Got it. Okay, great.
Yeah, and that's a good one to memorize because we do most things in dB as engineers in all fields. Audio, RF, dB is our friend.
Great. The rest of it I think is pretty clear. And then in the end, you just added all those numbers up and got your final number. And you said, hey, negative is good. That's up into the green number, right?
Yep. And I said we're gonna assume a little bit more loss from that, but we have that much power getting that negative 40 region. That loss is going to put us still in a very good area. So anywhere around that green, and we're good.
All right. So this is a lot of stuff. I know we went through this really quickly. I would love to see your example of a link budget, for your next show or a past show that you've done. And if you want to, draw it out, take a photo of it and post it here along with this video, we can see if we can get Steven to look at them and see if he thinks they're correct or if you estimated well. And some of the stuff you can grab. So if you're using a ULXD receiver, you can use the numbers that we used in this example. Otherwise, you have to look up each one for your specific situation. But Stephen, thank you so much for putting this together. And now I obviously need to practice doing it myself.
Awesome. Well, thanks for the opportunity, and this has been great. Hopefully, everybody takes a shot at this and has good results.
Sound design.